Okay, welcome back to the fifth and final installment of the Dell's Tech Physics 111 Exam 2 Preparation and Practice Exam covering forces and energy. And in this video, we're going to cover energies like kinetic energy, potential energy, mechanical energy, and non-mechanical energy. Okay, let's look at the problem. A 50-kilogram boulder falls from the top of a high cliff. So we can actually represent that with a really simple drawing over on the side here. You have a boulder, it's 50 kilograms, and 50 kilograms, because it's in kilograms, that's our mass, not the weight. We are given that G is 9.8 meters per second squared. We're not going to worry about the negative sign because all forms of energy are scalars and we're going to keep them as positive values. It says when the boulder is at 62 meters, so this height, it's falling. At some point, the boulder is at 62 meters above the ground, 62 meters. At this point, the boulder is now traveling at 15 meters per second. And of course, that's moving downward. All right. The boulder eventually lands and stops on the ground, on the soft sand at ground level, meaning 0 meters high. What is the kinetic energy at the 62-meter high position? Well, we have a very straightforward formula for kinetic energy. It's equal to 1/2 times the mass times the speed squared. Well, we know the mass, we know the speed, we can just plug these values in. 1/2 times the mass, which is 50 kilograms. Oops, try to make it a little better than that. 50 kilograms. Try this again, sorry. Pardon my penmanship here, 50 kilograms. And we're going to multiply it by not just the speed, but the speed squared. The speed at this point is 15 meters per second, so we have to square that first. So you're going to square that, you'll get just that would be 225, and we would square the units as well, meters squared per second squared. We'll just put that on the side. So we've got 1/2 times 50 kilograms times this new term, 225 meters squared per second squared. And we multiply this out with our calculator, and we get a value of 5,625. And yes, the units would be kilograms times meters squared per second squared, but that's just another version of joules. We know it's joules because every form of energy, including all of these plus work energy, they're all measured in joules. And as long as you use the international standard units like meters per second and kilograms and newtons, etc., in these formulas, you'll always calculate joules for energy. Okay, let's look at the next problem. What is the gravitational potential energy at that same position? Well, gravitational potential energy also has a simple formula for its calculation. It's gravitational potential energy equals mass times g, which we know is the weight, times the height. So if we were given weight, we wouldn't multiply it by the g, but we were given the mass, so we do have to multiply it by the g. Our mass in this problem is 50 kilograms. It hasn't changed. Our g is, we are told, 9.8 meters per second squared. And the height at this point in the drop is 62 meters. And we literally just multiply those out. Let's scroll this back up here. We multiply those out to get a value of 30,380. And again, we have these weird units of kilogram, meters, and there are 2 meters here, meters and meters, so it's meters squared per second squared, which we know is the same as joules, so this is 30,380 joules. So now we have our kinetic energy and we have our gravitational potential energy. So the third part of this question says, what is the kinetic energy after the boulder hits the sand? Well, after it hits the sand, we know the speed is now 0 meters per second. It's stopped. Our formula for kinetic energy is 1/2, just like we did it before, 1/2 mass times v squared. So it doesn't matter how big the mass is. Once you put a 0 in, you can stick the mass in here, kilograms. Once you stick 0 in for the speed and square it, it's still 0, and the whole thing just becomes 0 joules. Anytime an object stops, the kinetic energy is gone. So if you had just written kinetic energy is 0 joules, that would have been fine. A little explanation would help, saying that, oh, the velocity is 0, so therefore the kinetic energy is. Okay. And looking at this last one on this page, because there's another page here, what's the gravitational potential energy after it hits the ground? Well, gravitational potential energy, looking back at the formula we just used, mgh. Again, we have a mass of 50 kilograms. We have g, that's 9.8 meters per second squared. But if it's hit the ground at ground level, there is 0 height. There is 0 meters of height. And again, this whole thing becomes 0 joules. So both the kinetic energy and the gravitational energy are 0 if it stops, meaning no kinetic energy, and it stops at the bottom, at the very bottom. If it was to stop at a point higher, let's say there was a ledge here and the object dropped and it ended up here and stopped, the kinetic energy would be 0 because it stopped. But the potential energy, the gravitational potential energy, is not 0. It's still not 0 here. It's still above the ground level. It's got this much height, and you'd have to figure it out for that much height. So please be aware of that. Moving to the next page, it says, what's the mechanical energy at the 62 meter high position? Well, we know mechanical energy is a very simple formula. Mechanical energy is just the sum of kinetic energy and potential energy. Well, the only potential energy we're talking about here is gravitational potential energy. So we're just going to replace it with gravitational potential energy. So that's the sum of the first number we calculated. Let's scroll back up to that. That's 5625. 5625 joules for kinetic energy. And then we had another one that was about 30,380 joules for the gravitational potential energy. 30,380 joules. And then it's simply a matter of adding those two numbers up to get our total mechanical energy of 36,005. And that's our mechanical energy, this value here. The next question, part F, says, what is the mechanical energy after the boulder hits the sand? Well, again, we use the simple formula, mechanical energy equals kinetic energy, and we know that plus potential, but we know the potential is gravitational potential. We put those numbers in. We had 0 for the kinetic energy because it hit the sand, it stopped moving. And I specifically told you that it hit the sand at the bottom. So the gravitational is 0. If it was still moving, it would have some kinetic. If it was above the ground, we would have to add some gravitational potential at this moment. Part G says, how did the kinetic energy change during this time? Well, it went from 5,625 joules to 0 joules. Why? Because it stopped moving. It's as simple as that. No movement means no kinetic energy, so it decreased. And we'll just write decrease. A little note, decrease. The next part says, how did gravitational potential energy change during this time? Well, we started up at 62 meters high. We started with a gravitational potential energy of 30,380 joules, a very high number of joules, and it went to the bottom. It went all the way to the bottom. It didn't hit a ledge above and stop with a little bit of gravitational potential energy. It hit a position at the very bottom which had 0 potential energy. And that is because its height changed from 62 meters to 0 meters. It landed on the bottom. No height means no gravitational potential energy. So it also decreased in this case. But you know there's conservation of energy, so that energy had to go somewhere. We'll talk about that in a second. How did the mechanical energy change? Well, scrolling back, we calculated mechanical energy when it was still up in the air, 36,005 joules. So that's what it was while it was up in the air, 36,005 joules. And then when it landed, it lost its kinetic energy because it stopped. It lost its gravitational potential energy because in this case, it had hit the very bottom. So the total of those is 0 joules as well. So why did the mechanical energy decrease? Well, the height decreased, and that dropped the gravitational potential energy, and the speed decreased, that dropped the kinetic energy. And in fact, both of these decreased to 0. 0 meters or 0 meters per second for the height and speed respectively. Part J says, how did the non-mechanical energy change during this time? Well, we don't have a way to calculate non-mechanical energy directly, but we know that if all our mechanical energy went to 0, it had to go somewhere, and where it went to was the non-mechanical energy. So we know we had this much energy before it hit. Well, that much energy is pretty much going to be turned into non-mechanical energy. So how did it change? Well, it went from 0, or essentially 0. There might have been a tiny bit of friction in the air before it landed, but we know most of that ended up as a combination of sound energy, also called acoustic, heat energy when it landed. If it was a big rock hitting the ground, that's going to heat up the rock, it's going to heat up the ground, heat up whatever it hits, might heat up the air nearby, and it's going to deform whatever it landed on, or maybe deform the rock itself, or the block itself. So anything that breaks or bends something irreversibly, that's deformation energy. So we know we lost mechanical energy, so the non-mechanical energy must have gained that energy due to conservation of energy. Running out of room here. Conservation of energy. I'll just abbreviate energy that way. How did the total energy change? Well, the system includes everything in this case, so the total energy isn't lost. We lost mechanical energy, we gained non-mechanical energy, but if you add them up before you start, everything's in the form of mechanical energy, and when you end up, almost everything's in the form of non-mechanical energy. So it's the same total in the beginning, and I'll just circle, here's the total in the beginning, the mechanical and the non-mechanical in the beginning, 36,005 joules plus 0 is equal to 0 plus 36,005 joules. It's the same before and after. So the total energy remains constant. And we know that because of conservation. Now we can spell it out. Conservation of energy. And that is the end of practice exam 2. And I wish you luck when you take your exam.